Dr. Sasikumar sir.
Sir, good evening, sir.
Good evening, good evening. Thank you, sir. Thank you, sir. Thank you, sir. Dr. Suryakala, madam.
Yes, sir. Shall we start?
Oh,
5 o'clock.
no,
Only
3 minutes.
members.
3 minutes.
Okay, sir. Okay, sir.
Okay, okay, okay. Dear participants, please mute your audio and video mode, please. Miss Jayalakshmi, madam. Miss Jayalakshmi, madam.
Yes, sir.
Okay, okay. Thank you, madam.
Hi.
Dr. P.S. madam, you can start, madam.
Good evening, one and all present here. Today, the fourth day of International Faculty Development Program on current scenario in advanced material research and nanotechnology. On behalf of our management, principal, vice principal, and Department of Physics, a warm welcome to our chief guest today, Chief Guest Dr. Subramaniam Sasikumar, who delivered a speech on lead-free piezoelectric ceramics. On behalf of Department of Physics, I welcome all the participants. The presence today in this virtual platform is definitely very grateful to our department and Rajapalayam Rajas College. We are happy to invite you all. And I once again a warm welcome to one and all present here. Now I invite Ms. V. Jayalakshmi to introduce our chief guest, Dr. Subramanian Sasikumar.
Thank you, ma'am. Good evening.
I'm much delighted to introduce our today Chief Guest, Dr. Subramaniam Sasikumar. He did his PhD MPhil at Madura College, MSc in NMS Velachami Nadar College, and BSc in Saraswati Narayanan College. He received research fellowship by Nobel Research Board, DRDO, Government of India, from 2013 to 15. His research experience are tremendous. He was research scholar from 2015 to 18 in Madura College, postdoctoral research fellow under Curry Institution from 2018 to 19. He was a postdoctoral researcher in Government of China from 2019 to 21. He was research professor in Pukyong University of South Korea. He is a postdoctoral research in Korea Institute of Ceramic Engineering and Technology from 5/10/2022 to till now. He has flight skill and laboratory and instrumentation skill like multiferroic tester, piezometer, dielectric analyzer, electrical cooling machine, and computer software skill like Xana 2006, Prima Dinosaurmia 2014, Vesta. His list of publications are very encouraging to the young researchers like us. He published 26 international journals, and his list of book chapters are 3 in Material Research Form, Material Research Foundation USA 2016. He published more than 10 papers in the conference. We are very lucky to have you, sir. Thank you.
Thank you, ma'am. Can you hear me?
Sir?
Yes, ma'am.
Yes, sir. You can share the presentation, sir.
Sir, shall I start?
Yes, sir.
Okay. Good evening to all. Myself is Sigmar. I am doing a postdoc in Korea Institute of Ceramic Engineering and Technology, Jeonju in South Korea. Today I am going to deliver a talk on lead-free piezoelectric ceramic materials and some applications on the lead-free based materials. First of all, the introduction about my work is what is this material science? Material science is a interdisciplinary field applying the synthesis, characterization, and properties of material to various areas of science and technology, and then we are searching different type of properties like strength, hardness, flexibility, and the thermal and the magnetic and the electrical properties, stability of the material, and then catalytic properties, and the reusability, and the eco-friendly, and in the low-cost materials. In the low cost, based on the above properties applied in our day-to-day life, we are using so much materials. Then list of the materials: inorganic crystals, covalent materials, metals, alloys, semiconductors, superconductors, polymer materials, composite materials, ceramic, actually dielectric materials, and then inorganic classes and the catalysts. So we are going to give some introduction about the dielectric materials. What are the dielectric materials? Dielectric materials are classified into different two types. One is non-centrosymmetric material, another one is centrosymmetric material. The non-centrosymmetric material possesses the three different types of piezoelectric, pyroelectric, ferroelectric properties, and then centrosymmetric materials do not have any these properties because they are in a cubic nature. So other than cubic structure have the different properties. These some of the examples of different crystal structures are tungsten boson, perovskite structure, polychloride structure, bismuth layer structure. Among this material, perovskite is a well-known and many researchers are going through into that material. Some of the examples are barium titanate, sodium potassium niobate, lead zirconate titanate, and lead magnesium niobate samples are the examples of lead perovskite AbO3 structure. And then relationship between the piezoelectric, pyroelectric, and ferroelectric properties. Here I show the difference relationship between them. First one is piezoelectric materials is a mechanical force induces the polarization changes in that material. It is called the piezoelectric property, and then thermal energy induces the polarization is pyroelectric, and then electric field induced polarization is in terms of in the ferroelectric properties. Most widespread use ferroelectric material is in electromechanical devices via the piezoelectric effect. The piezoelectric effect is divided into two different types. First one is direct piezoelectric and converse piezoelectric materials. When you apply a stress into the material, it induces some polarization, and that means the separation of positive and negative charges. So it produces some voltage and gives to the output. So polarization is equal to D into stress. And then converse piezoelectric effect is when you apply electric field into the induces the strain into the in the material. It is the shape change, which will produce some vibrations in terms of output. So strain equal to D electric field. So the D is the piezoelectric coefficient. Its unit is picocoulomb per Newton for the direct piezoelectric effect and picometer per volt for converse piezoelectric. The piezoelectric coefficient is a third D33 in terms of third rank tensor material. For over 5 decades, irrelevant ferroelectric materials of choice for such applications are based on the lead zirconate titanate materials, BBZT3. Commonly, it is known as BZT materials. It is an alloy. It is a solid solution material of two compounds, BBTiO3 and BZRO3. However, presently there are great focus on the developing the lead-free piezoelectric materials instead of the PZT materials, and then high performance piezoelectric sensors. So the piezoelectric materials are used in the actuator applications, which are the mainly used as lead-based materials. Is BBTiO3, BBZRO3 with composition of some ratios and then some other compounds, and then lead-free piezoelectric ceramic is BATiO3, BAZRO3 and combination of CaTiO3 and LiSP modified sodium niobate oxide and sodium potassium niobate oxide and sodium bismuth titanate modified with the barium titanate is another one of the lead-free piezoelectric ceramics. Okay, then here this is the morphotrophic phase boundary of the BZT. BZT means lead zirconate titanate samples. So what is the morphotrophic phase boundary? The solid solution system shows composition driven interferoelectric instabilities in their respective composition. Some particular in some particular ratios, for example, x when you go to the x equal to 0.45 around 0.5, the sample possesses one or two structures, one and two different structures exist in one materials. The one is rhombohedral structure and another is tetragonal structure in particular one composition. It is the morphotrophic phase boundary of these BZT samples. A characteristic feature of MBP, or sometimes it called as polymorpho morphoric phase boundary (BBB) composition is coexistence of the ferroelectric phases. Say tetragonal and rhombohedral symmetries exist in one materials. This can be easily verified using the powder X-ray diffraction data sets. And then another one property is electrostain properties in the lead-based ceramic materials. Maximum electrostain reported in the lead-based piezoelectric ceramic is 0.03 to 0.04%. With the corresponding piezoelectric value is around 1500 picocoulomb per Newton for this composition. So whenever we have a high electrostain in that composition, it also possesses higher piezoelectric values. And then application of these piezoelectric ceramics, used in many applications: pressure sensor, accelerometers, energy harvesting from vibrations, spark generation, actuators, transducers, ultrasonic motors, fuel injections in the automobile. And then why I am going to for lead-free piezoelectric ceramics. Among the lead-based ceramics, it has higher piezoelectric and ferroelectric properties, which is mainly used in the sensors and the actuator properties. But all lead-based ceramics are the very toxic materials to compare to the toxic materials. It is used in the many electronic gadgets, which is disposed into the earth. It is very toxic to our environment and also very harmful to our human health. So we are going to next for the alternative for the lead-based piezoelectric ceramics is a lead-free piezoelectric ceramics. Among the various different lead-free piezoelectric materials, barium titanate, sodium bismuth titanate, sodium potassium niobate are expected to be the most promising substitute for the lead-based piezoelectric ceramics. And then the lead-free piezoelectric ceramics in 2019, the growth mainly used in many electronic gadgets like piezoelectric devices. In 2019, the growth rate is 6.2%. Now, in 2024, it will be rise 20.8% from 2019 to 2024. Thus, there is a good development in the lead-free piezoelectric ceramics. Then, brief introduction about lead-free ceramics. Okay, here is so that this is the BaTiO3 perovskite structure. Barium as a site, Ta is a B site, and oxygen as in the corner. So there are different structures: tungsten ozone, bismuth layer structure, polychlor, oxygen octagon. That is perovskite structure. Perovskite structure is a well-known material. It is developed so for many researchers. So the origin of the piezoelectricity and ferroelectricity in perovskite oxide is mainly depends on either BO6 octagon. B is a B site in center atom. The vibration of TiO bonding is mainly causes the piezoelectric and ferroelectric properties in the perovskite oxide materials. Here is this is one of the BaTiO3 and lead zirconium titanate oxide is one of the main examples of perovskite oxides. And then ferroelectric and piezoelectric related activities in our group. Here I listed some lead-free piezoelectric materials. There are sodium bismuth titanate based barium titanate modified lead-free piezoelectric ceramics and doped barium titanate oxide barium titanate materials, and the rare earth doped barium titanate based materials. Then is the experimental details of the lead-free piezoelectric ceramics is mainly all the materials been grown by solid state reaction method. Here I show one example is sodium bismuth titanate modified with barium titanate. Initially, the raw compounds are weighted as stoichiometric proportions and ball milled for different ball milled for 300 RPM for 24 hours, and then the ball milled samples are calcinated at 850 degree. Then the powder again for a pelletized for a pelletized and then sintered for 1150 degree. So at the calcination, the three rock compounds are mixed into a it forms the composition sodium bismuth titanate modified with barium titanate. The barium atom is occupied into the A site of AbO3 structure, and the titanium oxide is a B site of the AbO3 structure. And then final sintered pellets have high density pellets. It is used for the ferroelectric and piezoelectric characterization, and then for the electrode application, you have to apply for a silver paste on the top and bottom surfaces of the material, and then finally other characterizations like piezoelectric and ferroelectric characterizations. Okay, and then powder XRD analysis for sodium potassium niobate modified with barium titanate samples. Here it shows the 4 different compositions, x equal to 0.1 and x equal to 0.2 with the different white compositions. From x equal to 0.1 to 0.2, the composition is transferred into tetranylitic cubic structure. That is the one is a non-centrosymmetric to centrosymmetric compositions, which is evidenced from the splitting of the diffractions and around 46 theta. And then another one example is sodium bismuth titanate modified with barium titanate. This XRD X-ray diffraction patterns also shows the phase transition from rhombohedral to tetragonal phase. And then another third one composition is barium zirconium titanate and barium calcium titanate mixed with different compositions. For example, 0.4, 0.5, and 0.6 x equal to 0.5. So compared to 0.4 and 0.6 x equal to 0.5 sample possesses coexistence of rhombohedral and tetragonal structure. So this is considered as a morphotrophic phase boundary of this composition. Okay. Then microstructure and other ferroelectric and dielectric properties of this of the lead-based ceramic is the microstructural properties analyzed by scanning electron microscopic images, and then EDS spectra are used to find the elemental compositions in that compositions, and then tuck plot this is absorption spectra from the UV visible absorption spectra used to find the band gap of the prepared lead-free piezoelectric ceramics. And then here the dielectric spectra shows the phase transition and the Curie temperature of this composition, and then the graph between the plot between polarization and electric field shows the ferroelectric properties of this composition. The polarization values around 15 microcoulomb per centimeter square, and then the D33 this is the D33 meter. It gives the piezoelectric coefficient of the electric piezoelectric ceramics. And then this is the another one interpretation of from the powder XRD analysis is charge density analysis. The powder XRD analysis data is subjected to the ritual refinement, and then charge density analysis using the maximum entropy method. Here is the three-dimensional structure for the tetragonal structure, and then two-dimensional charge density varies on the 001 plane. Here I can correlate the charge density, mid-bond electron density to the ferroelectric and piezoelectric materials. So the higher amount of charge accumulation between the two titanium, niobium and oxygen atom, so gives more vibrations in that composition. So have higher polarization values compared to other compositions, and then it has higher D33 values. D33 values 120 picocoulomb per Newton is observed for the x equal to 0.1 composition. Then the 2D charge density distribution patterns of sodium bismuth titanate and modified with barium titanate compositions. So here the bonding between the titanium and the oxygen atom possesses higher mid-bond electron density 0.75. This is considered as a covalent bonding between the Ta and O oxygen atom, which also gives higher remnant polarization value compared to other samples. So, and then another one composition for barium zirconium titanate and barium calcium titanate modified samples x equal to 0.5 possesses higher ferroelectric property P max equal to 15.12 microcoulomb per centimeter, and then it possesses higher D33 value 276 picocoulomb per Newton. So this also one of the reason. So and correlated with the bonding between the titanium and the oxygen atom is higher mid-bond electron density values. This also considered as a covalency. The covalency between the Ta and O ions is mainly plays a main role in the ferroelectric and piezoelectric properties. So another one lead-free piezoelectric ceramics is sodium bismuth titanate, and then barium, and then doped with barium atoms, and the Ta atom is modified with yttrium and Sb atoms. This is the powder XRD patterns of the different compositions. When you add the higher composition, the peaks are shifted towards the lower angle side of 2 theta, and then residual refinement profiles of NBBT and yttrium and Sp doped materials. Here, this is the structural parameters of NBBT, yttrium sp doped material. And then this is the Raman spectra of this. So these materials around the Raman shift around in A site compared to A site and TiO1 site and TiO6 different number of different Raman modes are compared to the previous report is well established with these compositions. And then this is the PE loop and SE loop of NBBT doped with ETM and SP doped materials. Here the electric higher field of electric field is applied to that material, and then polarization around 35 microcoulomb per centimeter squared. Here the SU loop shows butterfly type loops for all the compositions, and then x equal to 0.02 composition possess higher strain value around 0.22% of strain is observed in that composition. This is mainly due to the both different structures is coexisted in that particular these compositions. And then this dielectric measurements of NBBT, ETM, SB doped materials for different composition. Here the dielectric spectra gives two different dielectric anomalies. First one, dielectric spectra around 150 degree is shows the TS is it is a shoulder peak, and another around another one dielectric peak shows around 300 degree. This is the Curie temperature of this material. The rhombohedral structure changed into the cubic structure, and then TS is mainly due to the nanopolar regions of the rhombohedral structures in that material. And then another one lead-free ceramic is calcium doped barium Ti 0.95 SN 0.05 based materials. And then here this is the powder hexagonal diffraction and cell parameters of different structures, and then the phase ratio of these materials are refined using the Ritval refinement. And then dielectric spectra, the VCST material have the dielectric properties were measured at low temperature from minus 75 to 150 degree Celsius. There is a three different dielectric anomalies. First one is Arbos transition, rhombohedral to orthorhombic phase transition, and another one is orthorhombic to tetragonal phase transition, and finally tetragonal to cubic transition. This is called as termed as Curie temperature. And then using this all the transition temperature, here I plotted the phase diagram of this composition. So around 0.4 composition possesses different two orthorhombic and tetragonal structure. So at the room temperature, the x equal to 0.04 composition possesses orthorhombic and tetragonal structures. So it is mentioned as a morphotrophic phase boundary of this composition. Okay. Then the plots of the ln of 1 by epsilon by 1 by epsilon max by ln of t minus t of BCST ceramic. This plot gives the gamma value of the different compositions. This gamma value is mainly indicates the relaxer properties of this composition. Whether this relaxer or not, non-relaxer material, we can easily find from the gamma values. The around one below around 1, so it is a non-relaxer material. After the gamma value is equal to, if the gamma value equal to 2, it is a good relaxer material. And then PU loop measurements of PCST. So polarization versus electric field plots is measured for different composition, and then the variation of this composition is mentioned here. The maximum polarization PR and P maximum and the higher value of coercive field is obtained for X equal 0.06 composition. This may be due to the composition nearer to the morphotrophic phase boundary of these compositions. And then SE loop of strain versus electric field measurements of PCST ceramics is mentioned for different compositions. Similarly, the X equal to 0.06 compositions also possesses higher electrostrain compared to other materials. And then we go for some rare earth doped barium titanate based solid solution. First one is neodymium doped barium titanate. The XRD profiles for the different types of neodymium doped shows the tetragonal structure with P4 space group, and then phase transition from tetragonal to cubic is observed in that material, and then retrieval refinement also plotted for these compositions, and then charge density distribution in two-dimensional place or the ND doped barium titanate materials used on different planes, 100 plane and 200 planes is shown here. And then one-dimensional charge density distribution gives the bond length between the BA and O and the TA and O, and then mid-bond electron density of these compositions. And then scanning electron microscopy and the EDS spectra of these composition, and then PL spectra of X equal to 0.04 compositions also shown here. The emission wavelength is 611 is consistent with the previous report. And then PE loop hysteresis loop is so here the highest value of polarization is observed in 0.04 compositions, and then the UV spectra gives the band gap values of the ND doped barium titanate also mentioned here. And then another one rare earth doped material is europium doped barium titanate materials. Here the raw powder XRD diffraction patterns of different for different compositions, and then the addition of europium composition in barium site, the peaks are drifted towards the lower angle side of 2 theta, and then retrieval refinement profile for this composition for the x equal to 0.00 composition, and then corresponding to the cell values is decreased when the addition of the European compositions. And then again, the charge density distribution are plotted in two-dimensional charge density distribution on 100 plane and 200 plane also mentioned here. And then one-dimensional charge density, similarly, in the previous work, it also gives the bond length between the BA and O and bond length between TA and O, and also gives the midpoint electron density values of these two bondings. And then UV spectra of europium doped gives the band gap values around 3 electron volt, and then PL absorption and emission spectra of these different compositions. These well correlated with the previous ones. And then significant outcome from these lead-free ceramic solid solution were synthesized by the solid state reaction method, and then powder XRD refinement and suggested the phase transition with respect to the addition of the BaTiO3 dopant in the host lattice, and then structural, morphological, and optical and photoluminescence and ferroelectric properties are investigated. And then charge density distribution and bonding features using the maximum entropy method, employing the experimental X-ray diffraction dataset. The correlation between the charge-derived properties and then ferroelectric and piezoelectric properties of the lead-free ceramics are also analyzed. And then the presence of covalentity and then covalentity in the BO atoms is mainly used to enhance the ferroelectric and piezoelectric properties. Among the different lead-free piezoelectric, PZT, BCT, x equal to 0.5 compositions is a higher value of D33 value, which is mainly attributed to the coexistence of rhombohedral and tetragonal phases in one composition, and it is found that most improved dielectric, ferroelectric, and piezoelectric properties occur near the MBP, actually morphotrophic base boundary region. Among all the compositions, lead-free piezoelectric ceramics, barium zirconium titanate, barium calcium titanate, x equal to 0.5 composition is the have better piezoelectric and ferroelectric properties. Might be a promising and lead-free piezoelectric material for various kind of actuators and transducer materials. So far, then we have developed so many lead-free piezoelectric materials, which is mainly used in the actuators and transducers, and then some sensor applications. And then, thank you for your attention. And then I would thank to the management committee, management of and authorities of the Rajapalayam Rajus College. And then I also thank to the convener of this program, and thank you. So please ask any questions and queries.
Dear participants, do you have any questions, please? Participants, do you have any doubts or any questions relevant to this topic? Please kindly ask any questions. Are you interested to interact anything to this, our chief guest today, Dr. Subramaniam Sasikumar? Rajesh sir?
Madam, we can wind up, madam. Please give vote of thanks.
Okay. So I'm so grateful to propose the vote of thanks for this today's International Faculty Development Program. I'm so happy. Today's information is very delightful and it is very useful to all the participants. So I'm on behalf of our management and the Department of Physics, I'm grateful to thank our chief guest today, Chief Guest Dr. Subramaniam Sasikuma. Thank you so much, sir. Your presentation is very good. There are so
Thank
many
you.
comments
Yeah.
also relevant to this one, sir. Thank you all the participants, those who are present virtual mode today present here. So thank you so much. Thank you one and all present here.
Thank you.
Rajesh sir. Rajesh sir.
Ma'am,
Rajesh sir is not here.